Hello and welcome. In this video, we will explore the scalar product, also known as the dot product, of vectors. This is a fundamental concept in vector algebra and is a key topic in the IB mathematics analysis and approaches higher-level curriculum. By the end of this session, you will be able to calculate the scalar product of two vectors, understand its geometric properties, and use it to solve problems involving angles and perpendicularity. Let's begin with the algebraic definition of the scalar product. Our first objective is to calculate the scalar product of two vectors. Let's start with the algebraic definition. For two vectors, A and B, in three-dimensional space, the scalar product, written as A dot B, is calculated by multiplying their corresponding components and summing the results. This operation results in a single number, or a scalar, which is why it's called the scalar product. Let's work through an example. Consider the vectors A equals 2, 1, 3, and B equals minus 1, 1, 1. To find their scalar product, we multiply the first components, 2 and minus 1, the second components, 1 and 1, and the third components, 3 and 1. Then we add these products together. This gives us minus 2 plus 1 plus 3, which equals 2. So the scalar product of A and B is 2. Now, let's look at some important properties of the scalar product. First, it is commutative. This means the order of the vectors does not matter. A dot B is always equal to B dot A. Let's prove this using our general vectors. We know A dot B is A1B1 plus A2B2 plus A3B3. Since multiplication of real numbers is commutative, we can rewrite this as B1A1 plus B2A2 plus B3A3. Which is exactly the definition of B dot A. This confirms the commutative property. Another key property relates the scalar product of a vector with itself to its magnitude. The scalar product of a vector with itself, a dot A, is equal to the square of its magnitude, or length. Let's prove this. By definition, a dot A is a 1 squared plus a 2 squared plus a 3 squared. We also know that the magnitude of a vector A is the square root of the sum of the squares of its components. Therefore, the magnitude squared is just a 1 squared plus a 2 squared plus a 3 squared. This proves that a dot A equals the magnitude of a squared. Finally, the scalar product is distributive over vector addition. This means A dot the sum of B and C is equal to A dot B plus A dot circa. Let's prove this as well. First, we find the vector B plus circa. Then we take the scalar product of A with this new vector. This gives us a 1 times B1 plus C1 plus A2 times B2 plus C2 plus A3 times B3 plus C3. Distributing the components of A, we get A1B1 plus A1C1, and so on. Rearranging the terms, we can group them into A1B1 plus A2B2 plus A3B3 plus A1C1 plus A2C2 plus A3C3. This is exactly A dot B plus A dot C, proving the distributive property. So, we have now seen how to calculate the scalar product algebraically and have proven its 3 key properties: commutativity, the magnitude squared property, and distributivity. These properties are essential for manipulating vector expressions. Now, let's move on to our second objective, understanding the geometric properties of the scalar product. This is where the scalar product becomes truly powerful. The geometric definition of the scalar product states that A dot B is equal to the magnitude of A times the magnitude of B times the cosine of the angle theta between them. This formula connects the algebraic calculation of the scalar product to the geometry of the vectors. Let's see how this formula is derived. Consider two vectors, A and B, originating from the same point. The angle between them is theta. We can form a triangle by drawing a third vector, B minus A, which connects the head of vector A to the head of vector B. We can apply the cosine rule to this triangle. The square of the length of the side opposite the angle theta, which is the magnitude of B minus A squared, is equal to the sum of the squares of the other two sides minus 2 times the product of their lengths and the cosine of the angle between them. Using our algebraic properties, we know that the magnitude of b minus a squared is equal to the scalar product of b minus a with itself. Expanding this gives us b dot b minus 2 times a dot b plus a dot a. We also know that b dot b is the magnitude of b squared, and a dot a is the magnitude of a squared. Now we can equate the two expressions for the magnitude of b minus a squared. Notice that the magnitude of a squared and the magnitude of b squared terms cancel out on both sides. This leaves us with negative 2 times a dot b equals negative 2 times the magnitude of a times the magnitude of b times cosine theta. Dividing by negative 2 gives us the geometric definition. A dot b equals magnitude a magnitude b cosine theta. This derivation is important because it shows the deep connection between the algebraic and geometric definitions. We have now established the geometric definition of the scalar product. Now that we have the geometric definition, we can use it to achieve our third objective, finding the angle between two vectors. By rearranging the formula, a dot b equals magnitude a magnitude b cosine theta, we can solve for cosine theta. This gives us cosine theta equals a dot b divided by the product of their magnitudes. This formula is incredibly useful. We can calculate the scalar product and the magnitudes of the vectors using their components, and then use the inverse cosine function to find the angle. Let's work through an example. Let's find the angle between the vectors p equals 2, 3, minus 1, and q equals minus 1, 0, 2. First, we need to calculate the scalar product, p dot q. P dot q is 2 times minus 1 plus 3 times 0 plus minus 1 times 2. This simplifies to minus 2 plus 0 minus 2, which equals minus 4. Next, we calculate the magnitudes of p and q. The magnitude of p is the square root of 2 squared plus 3 squared plus minus 1 squared, which is the square root of 14. The magnitude of q is the square root of minus 1 squared plus 0 squared plus 2 squared, which is the square root of 5. Now we can substitute these values into our angle formula. Cosine theta is p dot q divided by the product of their magnitudes, which is minus 4 divided by the square root of 14 times the square root of 5. This simplifies to minus 4 over the square root of 70. Finally, we take the inverse cosine of this value. Theta is the inverse cosine of minus 4 over the square root of 70, which is approximately 119 degrees. This is an obtuse angle, which makes sense because the scalar product was negative. This example demonstrates the complete process for finding the angle between two vectors using the scalar product. We have now met our third objective. Let's now focus on our fourth objective, using the scalar product to determine if two vectors are perpendicular. This is a very important application. We know that two non-zero vectors are perpendicular if and only if the angle theta between them is 90 degrees. Let's see what this means for the scalar product. If theta is 90 degrees, then cosine of theta is cosine of 90 degrees, which is 0. Substituting this into our geometric formula, a dot b equals magnitude a magnitude b times 0, which simplifies to 0. This gives us a powerful condition. Two non-zero vectors are perpendicular if and only if their scalar product is 0. This is a key result you must remember. Let's use this condition to solve a problem. We need to find the value of t such that the vectors p equals 3t and q equals minus 2, 1 are perpendicular. Since the vectors are perpendicular, their scalar product must be 0. So p dot q equals 0. Calculating the scalar product, we get 3 times minus 2 plus t times 1, which must equal 0. This gives us minus 6 plus t equals 0. Solving for t, we find that t must be 6. So, when t is 6, the vectors are perpendicular. This is a common type of problem in the IB exam. We have now successfully used the scalar product to determine perpendicularity. Let's now tackle a more complex problem that combines several of the concepts we've learned. This is a typical IB-style question. Consider triangle ABC with vertices A at 5, 1, 2, B at 6, minus 1, 0, and C at 3, 2, 0. We need to show that this is a right-angled triangle using only the scalar product. A triangle is right-angled if two of its sides are perpendicular. To check for perpendicularity, We need to find the vectors representing the sides and then check their scalar products. First, let's find the vectors representing the sides of the triangle. The vector AB is found by subtracting the coordinates of A from B, giving 1, minus 2, minus 2. The vector BC is C minus B, which is minus 3, 3, 0. And the vector CA is A minus C, which is 2, minus 1, 2. Now, we check the scalar product of each pair of vectors. If any pair has a scalar product of 0, the corresponding sides are perpendicular, and the triangle is right-angled. Let's check A, B.BC. This is 1 times minus 3, plus minus 2 times 3, plus minus 2 times 0. This gives minus 3, minus 6, which is minus 9. Since this is not 0, sides A, B, and BC are not perpendicular. Next, let's check BC.CA. This is minus 3 times 2, plus 3 times minus 1, plus 0 times 2. This gives minus 6 minus 3, which is minus 9. Again, not 0, so B, C, and CA are not perpendicular. Finally, let's check CA.AB. This is 2 times 1, plus minus 1 times minus 2, plus 2 times minus 2. This gives 2 plus 2 minus 4, which equals 0. We found a scalar product of 0. Since the scalar product of CA and AB is 0, the sides CA and AB are perpendicular. This means the angle at vertex A is 90 degrees, and therefore, triangle ABC is a right-angled triangle. This problem perfectly illustrates how the scalar product can be used to prove geometric properties. We have now seen a complete application of the scalar product in a geometric context. Let's look at another common type of problem, finding a vector with a specific length that is perpendicular to a given vector. The problem asks us to find a vector of length 10 units, which is perpendicular to the vector v, equals 3 minus 4. We'll solve this in 2 steps. First, we'll find any vector perpendicular to verses. Second, we'll scale that vector to have the required length of 10. Let's call the perpendicular vector u, with components x, y. Since u is perpendicular to v, their scalar product must be 0. This gives us the equation 3x minus 4y equals 0. We need to find a pair of x and y values that satisfy this equation. There are infinitely many solutions, but we only need one. A simple way to find one is to swap the components of v and change the sign of one of them. So if v is 3 minus 4, a perpendicular vector can be found by swapping the components to get minus 4, 3, and changing the sign of the first component to get 4, 3. Let's check if this works. 3 times 4 minus 4 times 3 is 12, minus 12, which is 0. It works. So u equals 4, 3 is a vector perpendicular to verses. Now for the second step, scaling this vector to the correct length. First, we find the magnitude of our perpendicular vector u. The magnitude of 4, 3 is the square root of 4 squared plus 3 squared, which is the square root of 25, or 5. Our vector u has a length of 5, but we need a length of 10. To scale it, we multiply it by the ratio of the desired length to its current length, which is 10 divided by 5, or 2. So our final vector is 2 times 4, 3, which is 8, 6. Let's quickly check our answer. The scalar product of 8, 6, and 3 minus 4 is 24 minus 24, which is 0. And the magnitude of 8, 6 is the square root of 64 plus 36, which is the square root of 100, or 10. Both conditions are met. We have found a vector of length 10 perpendicular to verses. Let's conclude with a final, more abstract problem that tests your understanding of the geometric properties. Suppose we have two vectors, c and d, with equal magnitudes. The magnitude of c is equal to the magnitude of d, and both are equal to the square root of 5. We need to deduce what we can about c and d if their scalar product is 5, and then if their scalar product is minus 5. We will use the geometric definition of the scalar product to solve this. The formula is c dot d equals magnitude c magnitude d cosine theta. Let's start with part A, where c dot d equals 5. We substitute the given values into the formula. 5 equals the square root of 5 times the square root of 5 times cosine theta. The square root of 5 times the square root of 5 is 5, so we have 5 equals 5 cosine theta. Dividing by 5, we get cosine theta equals 1. The only angle between 0 and 180 degrees, whose cosine is 1, is 0 degrees. An angle of 0 degrees means the vectors are parallel and point in the same direction. So we can deduce that C and D are parallel and have the same direction. Now for part B, where C dot D equals minus 5. Again, we substitute into the formula. Minus 5 equals the square root of 5 times the square root of 5 times cosine theta. This simplifies to minus 5 equals 5 cosine theta. Dividing by 5, we get cosine theta equals minus 1. The only angle between 0 and 180 degrees whose cosine is minus 1 is 180 degrees. An angle of 180 degrees means the vectors are parallel but point in opposite directions. So we can deduce that C and D are parallel and have opposite directions. This problem shows how the sign of the scalar product tells us about the angle between the vectors. A positive scalar product means an acute angle, a negative scalar product means an obtuse angle, and a zero scalar product means a right angle. Let's quickly recap what we've covered. We started with the algebraic definition of the scalar product, A dot B equals A1B1 plus A2B2 plus A3B3. We then derived the geometric definition, A dot B equals magnitude A magnitude B cosine theta. We saw how these two definitions are connected and how they allow us to find the angle between two vectors. Most importantly, we learned that two non-zero vectors are perpendicular if and only if their scalar product is 0. We applied these concepts to solve various problems, including proving a triangle is right-angled and finding perpendicular vectors. To solidify your understanding, here are 5 practice questions in the style of the IB exam. Pause the video, work through them, and then resume to see the fully worked solutions. Question 1. Find the angle between the vectors u equals 1, 2, minus 1 and v equals 3, minus 1, 2. Question 2. Find the value of k such that the vectors a equals 2k minus 3 and b equals 4 minus 1, 2 are perpendicular. Question 3. Given that the magnitude of p is 4, the magnitude of q is 5, and the angle between them is 60 degrees, find p dot q. Question 4. Show that the points A, 1, 0, 2, B, 3, 1, 1, and C, 2, 2, 3 form a right-angled triangle. Question 5. Find a vector of length 5 units that is perpendicular to the vector W equals 2, 1. Welcome back. Let's go through the solutions to the practice questions. For question 1, we need to find the angle between u and verses. First, we calculate their scalar product, which is 1. Then we find their magnitudes, which are the square root of 6 and the square root of 14. Using the angle formula, cosine theta is 1 over the square root of 84. The angle theta is approximately 83.7 degrees. For question 2, we need to find k for perpendicular vectors. We set their scalar product to 0. This gives us 2 times 4 plus k times minus 1 plus minus 3 times 2 equals 0. This simplifies to 8 minus k minus 6 equals 0, which means 2 minus k equals 0. Therefore, k must be 2. For question 3, we are given magnitudes and an angle. We use the geometric formula, p dot q equals magnitude p, magnitude q, cosine theta. This is 4 times 5 times cosine of 60 degrees. Since cosine of 60 degrees is 1/2, the scalar product is 4 times 5 times 1/2, which equals 10. For question 4, we check for a right-angled triangle. We find the vectors A, B, and BC. Their scalar product is 1. We find the vectors B, C, and CA. Their scalar product is minus 1. We find the vectors CA and AB. Their scalar product is 0. Since CA dot AB is 0, the angle at A is 90 degrees, and the triangle is right-angled. For question 5, we need a vector of length 5 perpendicular to W equals 2, 1. A perpendicular vector is U equals minus 1, 2. Its magnitude is the square root of 5. To get a length of 5, we multiply by 5 over the square root of 5 which is the square root of 5. So the final vector is the square root of 5 times, minus 1, 2, which is square root of 5, 2 square root of 5. I hope these solutions were helpful. Thank you for watching.